Hello everyone, welcome back to my channel. In this tutorial, I will show you how to calculate the energy barrier of diffusion of silicon vacancy in silicon crystal using non-rigid elastic band calculation, and I will use neb.x in quantum espresso. So I will split the tutorial into 3 videos, and this is the first video, and I will show you step 0, which is the preparation calculation, and I will first construct a 2x2x2 supercell. And because you know that for this kind of vacancy or defect calculation, you need to have as large supercell as possible, so that the defect does not see each other through the periodic boundary condition. And then I will take one silicon atom away to form a vacancy, and then relax the structure, and this is this will be used as the first image or the starting point in the next step. And then I will take another atom rather than the atom that I took away before. So still I will only take one atom away, but I take the atom that was neighboring away instead. And then I use this as the end point, or we say the last image in the next step. So the evolution or the energy barrier between these two images can be seen as the energy barrier of the diffusion of the silicon of the vacancy, because of the symmetry of silicon crystal. Yeah, so basically the movement between these two cases is the change of vacancy with the nearest silicon atom. And since because of symmetry, this exchange operation has the same energy barrier everywhere. So with that, the vacancy can move freely in the silicon crystal with the same energy barrier as I calculated here. Yeah. So in the next step, or we say in the next video, I will do a neb.x calculation to calculate the energy barrier without the climbing image to ensure convergence. Yeah, and then I will write the result here, and then in the last step I will refine the calculation using climbing image, and then I will write the result down there. Okay, so let's get started. Yeah. So those are the files for the first calculation. As usual, I will not really do the calculation because this is a large supercell, and the relaxation takes some time. Yeah. So I already did the calculation, and for the first input file, this is actually just a reference which contains the 2x2x2 supercell. Yeah. So this is a perfect 2x2x2 supercell, and I will later show you in XCrystal what is the structure. And then those two are the case when I take one atom away, and then those two are the case when I take another atom away. Yeah. I can first show you the input files, which you are more or less familiar with. The first thing is the perfect 2x2x2 supercell, and there are 64 atoms in the supercell, which is a large supercell, so we don't need that many K points, so that's only 4x4x4. That should be enough. And this no symmetry equals true means that we don't want it to have any symmetry, because for this relaxation calculation, if it detects some symmetry at the beginning, it will try to keep the symmetry and will not break it. So we specifically see that there's no symmetry. Yeah. Okay. So yeah. So that's it. And for the second input file, for this one we already took one atom away, so there are only 63 atoms. And I rearranged it a little bit so that everything, like every atom, matches the second vacancy here. So this is the atom that will be taken away in the second vacancy. And if we see in the input file of the second vacancy, you see that this is changed to another atom, but everything else has one-to-one correspondence, yeah, in the first and second vacancy, and this is very important. And I will show you the structure just in a second. Okay, and then we just start X crystal and pwscf and input file, and we first go to the reference, which is the perfect 2x2x2, and which is shown here. Yeah. So what I mean by 2x2x2 is that you can already see that basically from this, yeah, this is the usual unit cell of a silicon crystal, and basically I repeat this unit cell by 2 times in the x direction, 2 times in the y direction, and 2 times in the z direction. So that's what I mean 2x2x2. So this is not a small unit cell, but this is necessary. Yeah. Okay. And then what we want to do is that we want to like take one atom away. We want to take this atom away as the first image, and then for the second image we want to take this atom away. Yeah. So basically what it means is that in the first image we take this atom away, but we keep this atom, and in the second image we take this atom away but keep this atom. And then the energy barrier is basically the energy barrier that we move this atom towards this vacancy, yeah, which I will show you later. Okay. Yes. And then let's see what is the output file for the first vacancy, and out and animation. Okay, this time we choose this, and we see that indeed there is one silicon atom missing in the center. Yeah, and this current slide is 1, so basically this is before relaxation, and then we can play the animation to see how it relaxes. I don't know whether we can see or not, but basically the surrounding atoms shrinks towards the vacancy a little bit. Yeah, so which I can show you here. So we go back to the first image, and then go to the relaxed case, and you see that indeed it goes towards the vacancy a little bit. Okay, and then so this we use as our first image in the energy barrier calculation. And then let's check the second vacancy, which we can see here. And the center atom is actually here. So we actually take another atom away here, and let's play the animation, and you can also see that the surrounding atoms shrinks a little bit towards the vacancy. Yeah, so this we use as our last image. So basically the atom previously here moves to the center, and basically that means the vacancy moves in another direction here. And because of symmetry, the vacancy has the same energy barrier if it further moves here, and then moves here, and then moves here, and it has always the same energy barrier when it moves across the crystal. Okay. So so that's it for this video, and in the next video I will show you how to calculate energy barrier of this kind of transition between the first image and the last image. Okay, thank you for watching, and I hope to see you next time.